Imagine a world where planets could transform into black holes. Sounds like science fiction, right? But recent research suggests that this extraordinary phenomenon might actually be possible, and it could change our understanding of the universe. Exoplanets, once considered a niche topic in astronomy, have now become central to exploring the universe's mysteries. A groundbreaking study led by Mehrdad Faroutin-Mehr, a graduate researcher at the University of California, Riverside, along with postdoctoral researcher Tara Featheralf, proposes a fascinating theory. Certain gas giants might gradually accumulate dark matter in their cores, eventually leading to a collapse that forms a small black hole. The role of planets in dark matter detection. With thousands of exoplanets now cataloged, nearly 6,000 confirmed as of mid-2025, according to NASA's Exoplanet Archive, astronomers have a wealth of data to analyze. Gas giants, in particular, are ideal for this investigation due to their vast volumes and cooler interiors compared to stars, making any additional energy sources easier to detect. The research team modeled the behavior of heavy, non-annihilating dark matter as it interacts with a planet similar to Jupiter. They found that these dark matter particles would gradually lose energy, settle into the planet's core, and accumulate over time. Once this central mass reaches a critical threshold, the force of gravity takes over, causing the mass to collapse into a black hole. This black hole could either begin to consume the surrounding gas, or, if it remains small enough, evaporate. How planets might become black holes. The researchers specifically focused on scenarios involving super-heavy, non-annihilating dark matter. In this case, the captured particles do not eliminate each other, leading to a continuous buildup. Under these conditions, the core of a gas giant could collapse within observable time frames, and this process could potentially happen multiple times throughout the planet's life if dark matter capture continues. In simpler terms, if the right conditions are met, a planet with the mass of Jupiter could quietly evolve into a black hole of the same mass, retaining its gravitational pull but losing its physical form. Faroutin-Mehr emphasized, as the concentration of dark matter increases in gaseous planets, a black hole may form and start to accrete surrounding material. Discovering a black hole with the mass of a planet would be a significant breakthrough. Identifying planetary black holes. Interestingly, a planet that has transformed into a black hole would still exert gravitational influence on its star, meaning that signals such as radial velocity and astrometric measurements would remain detectable. However, the telltale signs of transits, where a planet passes in front of its star, might disappear, as the black hole would shrink to a size too small to create a noticeable silhouette against the star. This discrepancy presents a unique opportunity for astronomers. If they observe stellar wobbles indicating a massive planet, but find no corresponding transit dips, it would warrant further investigation. Microlensing offers another perspective. A compact black hole and a larger planet of the same mass would bend light in similar ways during microlensing events, making it challenging to distinguish between the two based solely on light curves. Population statistics could also provide insights. If numerous high-mass planets near the galactic center show signs of dynamical activity but lack transit signals, it would be difficult to attribute this pattern to chance alone. How telescopes can investigate? The upcoming Nancy Grace Roman Space Telescope is set to conduct a galactic bulge time domain survey, which will capture thousands of microlensing events in areas rich in dark matter, precisely where this model predicts stronger dark matter capture and faster collapses. By combining microlensing data with precise astrometric measurements, scientists can identify compact objects with planetary masses and map their distribution. If these planet-mass black holes cluster in regions of high dark matter density, it would lend significant support to this theory. Additionally, there is a thermal aspect to consider. Previous studies have indicated that dark matter annihilation could heat exoplanets, causing them to emit more infrared radiation than would be expected from cooling alone. Small black holes might also evaporate through a process known as Hawking radiation, releasing high-energy particles either into the planet or into space if they escape. Both scenarios could provide detectable signals, although current instruments may not be sensitive enough to capture the faintest cases. Limitations of the theory. However, it's important to note that this theory does not imply that all gas giants are destined to become black holes. Several factors must align, including the mass of the dark matter particles, their scattering cross-section, and the local density of dark matter. The absence of planet-mass black holes would also yield valuable information. If Jupiter-like planets remain intact in areas where the model predicts collapses, it would challenge our understanding of dark matter properties. The researchers also highlighted the necessity of employing multiple observational methods. No single transit, lensing event, or velocity measurement can definitively answer the question in isolation. There are also physical limitations to consider. The timescales for capture and drift depend on the temperature and density profiles within the planets, which are still subjects of debate. Even slight variations in these parameters can significantly alter the predicted outcomes. The significance for dark matter research. This research has the potential to transform standard planetary surveys into experiments in particle physics. As we gather data in our quest to discover new worlds, the confirmation of a planet-mass black hole would point directly to a non-annihilating, very heavy particle candidate, pushing the conversation about dark matter beyond the limits of conventional terrestrial detectors. Even a lack of findings would refine our understanding. If transit catalogs remain consistent with radial velocity and astrometric data, the absence of expected collapses would help constrain the properties of dark matter. This framework encourages new cross-checks as the catalog of exoplanets expands. The Roman Space Telescope's findings, combined with follow-up observations from ground-based observatories and future direct imaging missions, will set the stage for a definitive test of these intriguing ideas. The study has been published in the journal Physical Review D, marking a significant step forward in our quest to understand the universe's hidden components. Did you find this exploration of dark matter and planetary black holes intriguing? We'd love to hear your thoughts. Do you agree with the potential for gas giants to become black holes? Or do you think this theory is too far-fetched? Share your opinions in the comments below.